On April 28, 2021, Parker Solar Probe crossed a line that no spacecraft had ever reached, and nobody knew exactly where it was. The Alfvén surface, the invisible boundary where the sun's gravity and magnetic field stop controlling the solar wind and the solar wind breaks free. It's where the sun ends in every meaningful physical sense. Parker didn't just skim it. It crossed through, spent time inside, and came back out. Then, it did it again. And again. What it found on the other side of that boundary is a problem that 70 years of solar physics could not explain. In 1958, a physicist named Eugene Parker published a paper predicting that the sun continuously emits a stream of charged particles in all directions. He called it the solar wind. The paper was nearly rejected. The reviewers thought it was wrong. It wasn't. We now know that the solar wind reaches every planet in the solar system, shapes their magnetospheres, and drives the aurora on Earth. When it's strong enough, it can knock out power grids and disable satellites. But here's what solar physics never solved in the decades after Parker's prediction. Where exactly does the solar wind come from? And how does it get accelerated to 400 to 800 kilometers per second by the time it reaches Earth? The corona, the sun's outer atmosphere, the layer that becomes visible during a total solar eclipse, is paradoxically hotter than the surface below it. The surface sits at around 5,500 degrees Celsius. The corona reaches temperatures between 1 and 3 million degrees Celsius. Heat flows from hot to cold. That's a fundamental principle of thermodynamics. So why is the corona hundreds of times hotter than the surface it sits above? No one had a satisfying answer. Several theories existed. Alfvén waves carrying energy from the surface, magnetic reconnection events releasing heat, nanoflares too small and fast to observe directly. All of them had some evidence. None were confirmed. The answer was locked inside the region closest to the sun, a region that every previous spacecraft had been physically unable to reach. Parker Solar Probe was built to go there. When it crossed the Alfvén surface in April 2021, at roughly 18.8 solar radii from the sun's center, approximately 13 million kilometers from the surface, it entered a region where the physics is fundamentally different. Inside that boundary, the solar wind hasn't fully formed yet. The plasma is still magnetically connected to the sun. Waves can still travel back toward the surface. Outside, the wind is moving too fast for any signal to travel back. The sun loses control of its own material at that line. What Parker found inside upended the existing models. The data showed thousands of magnetic switchbacks, rapid, violent reversals of the solar magnetic field that flipped direction within seconds before snapping back. These weren't small fluctuations. Some of them bent the magnetic field back toward the sun by more than 90 degrees, creating S-shaped kinks in what should be a relatively organized structure. They were constant, pervasive. Something was folding the magnetic field at extraordinary scale, at extraordinary frequency, close to the sun's surface. The leading interpretation is that these switchbacks originate from interactions between rising plasma jets, called spicules, and the coronal magnetic field. When these jets slam into the field lines, they release energy that propagates outward in the form of switchbacks. That energy heats the plasma it passes through. And as it dissipates moving outward, it may be doing exactly what the corona heating mystery requires, depositing energy into the atmosphere far from the surface, where no direct heating from below should reach. Parker also measured the solar wind at speeds and densities near the sun that no model had accurately predicted. Close to the Alfvén surface, the wind was structured into thin, high-speed streams, jets of plasma moving faster than the surrounding material, traceable back to specific features on the sun's surface, regions called pseudostreamers and coronal holes. The picture that's emerging is not a uniform solar wind blowing evenly in all directions, but a structured, dynamic flow with identifiable origins and discrete features on the corona. In December 2024, Parker made its closest approach yet, 6.1 million kilometers from the solar surface, moving at 692,000 kilometers per hour, roughly 0.064% of the speed of light, faster than any human-made object before it. The data from that pass is still being analyzed, but early results confirm the switchback phenomenon intensifies closer to the Sun. The magnetic field near perihelion is more turbulent, more structured, and more active than any model from the pre-Parker era predicted.
Here's why this matters for anything beyond Earth orbit. The solar wind is not background noise for deep space missions. It's an active threat. Galactic cosmic rays are a chronic radiation risk that accumulates over months. Solar particle events are acute ones, sudden bursts of high-energy particles that can deliver a radiation dose in hours equivalent to a lifetime occupational limit for nuclear workers on Earth. The difference between a survivable mission and a catastrophic one is often timing. Whether the crew has 24 to 48 hours of warning to get into a shielded compartment before the worst of it arrives. Before Parker, space weather forecasting relied on instruments positioned at Earth, roughly 150 million kilometers from the Sun. Parker is collecting data 6 to 13 million kilometers from the surface. That's a 10 to 25 times improvement in proximity. When a solar particle event originates at the Sun, Parker detects it within minutes. Earth, or a spacecraft en route to Mars, won't feel it for hours to days. That window is the margin. What Parker is building is not just scientific knowledge, it's the observational foundation for forecasting systems accurate enough to make crewed deep space missions manageable. If a model trained on Parker's data can predict the intensity and trajectory of a major event 24 hours before impact, the radiation risk to astronauts on long-duration missions drops from probabilistic catastrophe to something plannable. That's the actual use case, not abstract physics, but a practical tool for keeping people alive between Earth and Mars. Parker also clarified the structure of the heliospheric current sheet, the vast rotating spiral of magnetic polarity that extends from the Sun outward through the entire solar system, and which spacecraft and astronauts will cross repeatedly on any long-duration mission. Close to the Sun, the sheet is more dynamic and irregular than models showed. Understanding its geometry at the source produces better predictions of how solar disturbances travel outward. That translates directly to improved forecasting accuracy for missions that will spend months in deep space. The corona heating problem hasn't been definitively closed. Switchbacks are the leading candidate, but the energy budget hasn't been fully confirmed. Scientists haven't demonstrated that the energy carried by switchbacks is sufficient to account for all the observed coronal heating. Alfvén wave dissipation remains in the running as a secondary or parallel mechanism. The answer may involve both in different proportions across different regions of the corona. The solar wind acceleration mechanism is better understood, but still not fully characterized across different stream types. Fast solar wind, originating from coronal holes, and slow solar wind from pseudostreamers and helmet streamer belts appear to form differently and accelerate differently. Parker's data is narrowing the problem, but the full picture requires more perihelion passes and more data from different phases of the solar cycle. Parker's mission is currently planned to run through at least 2025. Each orbit brings it slightly closer to the Sun. Whether the mission gets extended beyond that, and whether a successor instrument is funded to replace it, remains an open question. The science being returned is, by any measure, extraordinary. The infrastructure for converting that science into operational space weather forecasting tools is still being built. For 70 years, the solar wind was something measured at a distance, a river observed from the far bank, never from the source. Parker changed that.
Crossing the Alfvén surface is the equivalent of moving from studying a river at its mouth to standing where it begins. What's up here is faster, more turbulent, more structured than anything the models said. Eugene Parker died in March 2022 at the age of 94. He spent most of his career watching a theory he nearly couldn't publish become one of the central facts of astrophysics. The spacecraft carrying his name had already crossed his sun's hidden boundary once by then. It's crossed it more than a dozen times since. Each time, it brings back data from a place no instrument has been before. And each time, the sun turns out to be more complex, more active, and more consequential for the future of human spaceflight than the models predicted. The boundary is crossed. What's inside it is still being worked out.